Okay, so welcome, and now we're going to start our study of vector spaces. And of course, with any subject, we want to start with the definition. What is a vector space, right? So here's where we're going to start, and this is where we're going to start getting into a little bit more in depth as we go along. So we've spent the last several videos going through operations and developing the idea of matrices or a system of linear equations, and looking at free variables and the dimensions of that. So now we're going to start going into the next step, which is studying of vector spaces. Okay, so the definition of a vector space over the reals consists of a set V along with two operations, and again I got these in quotes because I don't want you to confuse these with regular adding and subtracting or multiplication that we've seen with real numbers. Okay, so I put these in quotes to let you know that it is an addition, but it's not necessarily the addition that we think about. So with these two operations, a plus and a dot, right? So you can think of these as addition and multiplication, but again, it's going to be nuanced and different than what we think sometimes. Okay, so we have a set V along with two operations, plus and dot, so addition and multiplication, subject to the conditions that all of these vectors, V, W, and U, that are in the set V, and all scalars, R and S, that are in the reals, that follow. So all of these conditions must follow. Now there's two more conditions. There are 10 conditions altogether. I'll have to write those out separately. But here are the conditions. V, the set V is closed under vector addition. Okay, what does that mean? It means that any two vectors in the set V that you add together will give you another vector that will be in V. So you will never get a vector, when you add two vectors in V, you will never get a vector that's outside of V. Okay? 2, vector addition is commutative. So it doesn't matter which order that you add vectors, you'll get the same vector. Vector addition is associative. So if you are adding 3 vectors, let's say, doesn't matter if you add the first 2 first and then the third one, or if you add the last 2 first and then the first one, right? Just like, think about the associative properties and stuff that we deal with the real numbers, okay? 4, there is a 0 vector in the set V such that when you add a vector to the 0 vector, you get the same vector. Okay? And this is true for all vectors in the set V. And then 5, each vector in V has an additive inverse, which means an additive inverse in, well, let's say the vector W, that when you add those two vectors, you get the 0 vector. So that's what we mean by an additive inverse, like in adding regular real numbers, right? We have an additive inverse in the reals, the negative numbers, right? So positive and negative numbers. So again, what we're saying here is there is a vector V. For any vector in V, there is an additive inverse such that when you add W and V together, you get the 0 vector. Okay, so that's what we mean. 6. The set V is closed under scalar multiplication. So that's when we multiply scalars together, real numbers together, or when we multiply a scale, in this case, when we multiply a scalar by a vector. Okay, so it's closed under scalar multiplication. So if you multiply any vector any vector in V by a scalar, you'll get another vector in V. That's what that's saying. You'll never get something that's outside of V. 7, scalar multiplication distributes over scalar addition. So if you're adding two scalars together, and you're multiplying that sum by a vector. You can distribute the vector over the addition, right? And then likewise, 8 says scalar multiplication distributes over vector addition. So if you're adding two vectors and you're multiplying that sum, quantity sum, by a scalar, you can distribute the scalar over the addition. Okay? Now, 9 and 10. Okay, so 9. 9 says ordinary multiplication of scalars associates with scalar multiplication. So ordinary multiplication associates with scalar multiplication. So what does this mean? It means that if we have two scalars, right? So if we have two scalars, very similar to what we were just talking about addition, right? The distributive property. So here, if we have R times S, times vector V, then we can group these like so. And so that's what we mean by associates here. Now, multiplication by the scalar 1, okay? So this is where we get the multiplicative the multiplicative identity, right? It's the scalar 1 multiplied by any vector is the identity operation, okay, or the multiplicative identity, what we call it. So we could take this scalar and we multiply that by any vector and it gives us back that vector. So the multiplication by the scalar 1 is the identity operation. And that's it. Now be careful. So just a remark, there are two kinds of multiplication and additions that's going on here. Okay, so just be careful with that. Okay? Is there anything else I'd like to say? Yeah, so the best way to understand this is to go through examples. So let's go through some examples. And so all vector spaces must satisfy these 10 conditions. Or let me explain this way. Any set of vectors must satisfy these 10 conditions to be considered a vector space. All right. Have a great day.